Yeah, thanks. Well, good afternoon, everyone, and thank you for joining us. My name is Keegan Ebbets. I'm with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring this Passive House and all electric homes training series to you all. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House and Build Green Connecticut. Today's training will be recorded and posted to our online video library afterwards. And as a reminder, as part of this training and workforce development initiative, we also offer a 75% cost reimbursement for individuals pursuing either FIAS or PHI, professional passive house accreditation, which includes the cost of the training and the exam. And once you become certified, you can submit your reimbursement application and we'll process that 75% reimbursement. If you have questions about the reimbursement application process or the incentive there, you can contact us at the email address on the slide here. Luke, if you want to go to the next slide. So in addition to the no-cost educational training series and professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to go all electric with their residential building projects or who pursue passive house certification in multifamily projects with 5 units or more. The passive house incentive design shown here on the slide includes pre-construction incentives for feasibility studies and energy modeling and post-construction incentives up to 100% of the cost of full passive house certification, capped at $1,500 per dwelling unit. One more, next slide, Luke. And the all-electric and high-performance certification bonus incentives are available for both single-family and multifamily buildings. There are 3 incentive tiers that projects can qualify for, with different performance criteria for each, as you can see here on the slide, and incentives that range from $1,500 a unit for multifamily buildings up to $12,500 for single-family homes, in addition to adder incentives for high-performance heat pump equipment and certifications such as Energy Star Tier, LEED, and DOE Efficient New Homes Program. Our goal is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you're interested in learning more, please visit our website or contact us at the number shown on the slide. Now, for some details on today's presentation, you can use the Zoom Q&A feature to communicate questions to our presenter, Luke, throughout. And as a reminder that today's session is approved for AIA, Health, Safety, and Wellness CEUs. So we'll communicate directly with those interested in the CEUs about that. And with that, I will introduce today's speaker. Luke Albin is a senior architectural consultant for Alpen High Performance Products. He's been in the building material field for over 20 years, focusing on the commercial market segment, and primarily works with design professionals to achieve their vision and purpose on projects. So, Luke, with that, I will let you take it away.
All right, thank you very much, Keegan and Sarah, again for hosting and all the participants for joining us today. What we're going to be talking about specifically is emerging high performance glazing technologies. As we as building codes evolve and as the landscape, as you all very well know, changes is changing very rapidly. Both windows and fenestration in particular are one of those levers that are very important within the building. So as I go through here, they're just required slides. This is a copyrighted presentation. As Keegan mentioned, this is AIA certified for the HSW credit, and we'll get those loaded in for you. But yes, so what we'll be talking about today, as I mentioned, evolving energy standards are changing very rapidly, particularly within our climate zone. Being one of the cooler in the United States, is kind of the ground zero of where these changes are happening. What we're going to look at really where the glazing industry was, where it is now, and then some really cool new products that are in the market in varying degrees right now, that are available to help with your building envelope. And really taking a look at kind of pros and cons of potential pros and cons of each one, by really diving into what those metrics are. So as I mentioned, we're going to be looking at insulated glass performance. There are some. This course is really revolves more around the glass itself. There is some information on frames and other window materials, but really how the glass interacts with the building, and what those fundamentals are, and what we have in the market now that's really cool new technologies. So we'll start off with a quote from Amory Lovins. If you don't know who he is, I usually ask, you wouldn't be the first to say that you are unaware. But he is you see here, an American physicist. He was a co-founder of the Rocky Mountain Institute, which is a think tank which advises the Department of Energy on a lot of their building codes throughout the country, and has been doing it for decades. But his quote, all of the energy pumped through the Alaska pipeline each year goes literally out America's windows. So, as a window manufacturer representative, it's kind of like, this is a pretty this is a pretty strong statement. So first inclination would be to say, defend against it. But when we take a look at glass and windows themselves, what we're looking for are a bunch of different things. We're asking the windows to do a lot of things. We want to be able to see out. Obviously, nobody wants to sit in a dark room all day. So we want to be able to bring the outside in, as they say. With that comes thermal insulation, the comfort of the building occupants. That includes keeping everything from sound, UV rays, condensation, potential condensation issues, all of those things being managed by the windows themselves. But has to tie into the building. Um, if many of you worked on FIAS projects or other high performance buildings, you know that that is a very thermal bridging and or the lack of thermal bridging is really the goal with this, and the windows have to do that. They have to be very good insulators themselves, really become part of the building envelope with their coordination with the air vapor barriers, and of course keep the weather out. So on this slide, there's really two numbers to look at here. I would forward you to this is a U.S. Department of Energy Building Technologies office put this out. Windows typically account for 8% of the envelope area. That includes the roof, the walls, everything there, but accounts for 45% of the envelope heat transfer. Pretty unbalanced. So thinking back to that quote from Amory Lovins, it's really hard to defend when Windows have a such an opportunity to be a real driver of energy savings, and of course energy use savings. Heat transfer. Why are we concerned about it? Well, again, we're in the cooler climate zone, so we want to keep the heat in. Our heating season is much longer than most others, and heat transfer really occurs through three ways. Conduction, which is through solid surface, so that's where the frame of the window comes in to play. What is that frame made out of? Is it wood? Is it fiberglass? Is it vinyl? Is it aluminum? Is it thermally broken? A lot of factors happen there. Also, the insulating glazing unit spacers themselves. So what is the solid material around the edges of the insulated glass unit? Those are made of different materials. Those also have different rates of heat transfer. Convection. So convection and where that lives within the windows themselves are in between primarily in between the insulated glass unit themselves, in between the panes. So what we do is we use gases that are more dense than air. So as heat tries to travel through the assembly, it slows down with those more dense gases. And then radiation. We will also want to be able to capture the passive heating nature of the sun. So radiation is can also equate to heat, radiation out as well as radiation in. So we manage that primarily with low E coatings within the glass. I'm sure all of you have seen these window stickers that are on all new windows. This is from the National Fenestration Rating Council. And it really is just a snapshot of the thermal performance of the windows. So just to dive into these briefly, U factor. So U factor is the insulating capability of the window. It is a ASTM test. Uh, those test parameters are 70 degrees inside, 0 degrees outside, 15 mile per hour sustained winds, and then that insulating capability is measured. The U factor is simply the inverse of the R value. So, for example, in this example, we've got the U factor of 0.22. That's going to be just shy of an R5 window. You'll notice in the thermal image, this is from the outside looking in. You can see with the thermal image, the orange red areas, that is where heat is being lost from the building to the exterior. We're real close to those ASTM uh, numbers here, or test parameters. So, but you see the orange red areas are where we're losing heat. Solar heat gain, again, this is going to be managed by the low E coatings. As I keep mentioning here, we're in a cooler climate zone. So we want to take advantage of the passive heating of the sun, whereas, Florida, Texas, New Mexico, all those, they want to do the exact opposite. Their cooling seasons are so much longer than ours. They actually want to keep that heat via radiation out, and we manage that with the low E coatings. And solar heat gain is that metric. Visible light transmittance, you see here, this is measured at 0.51. That is our percentage. So that would be 51% of the visible light is transmitted from the outside to the interior. I will note that when you get these on a window, that does include the frame, which you can obviously not see through. So, taking a look at visible transmittance in this format includes the frame, but there are also separate glass only or insulated glass only metrics. You may see it as COG or center of glass values, your visible transmittance. So this visible transmittance of the glass in this window, factory assembled is going to be 0.51. It may be 0.65 for the glass alone. So something to keep in mind when you're looking at specifying glass specifically. Just really touch on air leakage. This is a very um, basic air leakage here, point 3 CFMs. When we're looking at high performance building, we're more looking at the 0.03 and below, particularly with even operable windows. Fixed windows are like 0.01 and less. And then lastly, we have condensation resistance, which, believe it or not, is optional to be posted on these NFRC labels, but has the ability to be, I won't say it is, but it has the ability to have or to be one of the more overlooked thermal performance metrics when we're looking at windows. You see the number here is 51. The higher that number is, the better the condensation resistance is. Condensation, and hopefully nobody has a situation in their own home where they have this picture here where you see water on the interior. I do, unfortunately. Usually it happens in the fall when you turn the heat on for the first time. It's really a relationship between the relative humidity within the building, the center of glass temperature, but also what's going on outside. What's the dew point? There are a lot of different factors, but primarily the relative humidity within the dwelling, as well as the surface glass temperature, are really what drives the could be the preponderance of condensation. Just to give an idea of what the recommended air numbers are, just in some major US cities, you'll see. So, say for example, relative humidity within the building is at 40. Looking here in Atlanta area, this would do a good job, 50, 51%. They're looking at about 50. I'm located here in the Boston area, so we're really closer to 60. And as you get even more cooler climates, you see it approaching mid 60s, even 70 in Minneapolis from recommended condensation resistance factor number. So something to keep in mind. I'm sure all of us have, hopefully not seen them in our own homes, but, even out at, in stores or what have you, or restaurants, unfortunately see that condensation issue. So when we're looking at a window itself, and again, for those who have worked on FIA's projects, you'll notice that if you go to their certified window database, you'll notice that really some key performance components are pulled out and measured separately. The frame, the center of glass, and then the edge of glass itself. So as we take a look at kind of the building codes and again, where we were and where we are now, take a look at Energy Star, for example. A little over 10 years ago, Northern Climate U factor, 0.30. Any solar heat gain was sufficient for an Energy Star rated window. Um, Fast forward to today, and now we're at a 0.22 with a recommended solar heat gain coefficient. May not seem like a big jump, but if you take a look, well, 0.08 when you're talking about U factors, but remember when we're thinking about R value too. So your R value of that window, say a dozen years ago, is about a R 3.3. Now we're looking at an R almost 5 window. That's a pretty significant jump, particularly for domestic manufacturers who have standardized on the geometry of a dual pane window system. That 0.22 number really reflects very close to the limit to which dual pane products can be, particularly again in our cooler northern climate zone. For Canada, just as a base point, it's a little even more aggressive. So last year, all their residential windows, when you can do their conversion, they're looking at a U factor of 0.21, and by 2030, their goal is to be at a 0.14. So 0.14 is you are 100% out of a dual pane system. Some customers even looking at not only triple pane but quad pane windows to try to get to that number. But there are a lot of different strategies to get to that number. Adoption of glazing technologies. Again, we're talking about where we were. So taking a look back at 1970, and you'll see on the let's see if I've got a little. I do. This gray line here, single clear glass, about 90% of the market. There is still, by the way, a tremendous amount of building of stock out there in buildings right now, particularly commercially, that is just single clear piece of glass. It really wasn't until, and you'll notice, late 70s, early 80s, where this blue line, a double clear glass pack was used, really in response to the energy crisis here in the United States of the late 70s, early 80s, in the oil embargo time. Fast forward to the mid 90s, is really where the low E coatings took effect, and that's where we are today. Now, close to 90% is double low E coated windows. There is, you'll see here a little line for triple low here, little tick up. Primarily driven. Now there are some early adopters and those that find the value in putting a better window within their buildings, um, but driven by code. And that's where we see things. I know just going back uh, to Keegan's previous slide, really we're seeing not only the codes changing, but also the incentives are really robust enough to be able to pull in a much better high performing window. So when we look again, typical dual pane, you've got the exterior here. This gray portion is a low E coating, or the way that it's depicted. That would be surface two. So as we number these, it's one, two, three, and then four is the most room side on the dual pane. So this is showing a single low E coating on surface number two. How do we what the put when we put these windows in, how does it affect the overall wall assemblies? So I know we're always trying to strive to get to a certain window to wall ratio. Well, as we take a look here, and this chart will show as we are looking at the average wall value, and then on the horizontal axis here, you've got the window U factor. So we're starting off at zero point 0.3, and as you move from left to right, you get a better performing window. So this is a 10% glazed area. So you'll see a R20 wall, R30 wall, and an R40 wall. But as you increase, just kind of like to pay attention to this area here, between the 0.20 and the 0.15. As we move up from 10% to 20%, to 30% glazing ratio, you'll really notice, and as I back off here a little bit, you really can see where the windows are getting closer to the walls R value. So you really have more of an exponential benefit to using higher performing windows to get closer to the walls. So as you see here, 20% and then 30%. So it really isn't, and this is where primarily high performance windows will start off between this 0.20 and below. Again, because of the relationship with the wall itself. So this is the only question here that that we have in this presentation. But if we take this example, if we have a wall that is R20 wall, 50% glazing area, and a window U factor of zero point 0.3, which again, if you think about it, it's an R3.3 window. What would that overall assembly of the wall be when you take in this equation here that you see? Well, we find that with the R20 wall and an R, again, 3.3 window, the window has drugged this entire assembly down to a R 5.7. So pretty significant difference there. Here's just a typical example of an R20 wall, detailed out. But we want to get better performance out of our wall assembly. So what we're going to do is we are going to use R40 wall insulation. 50% same glazing area, 50%, same window U factor of 0.30. So when we do that, you see here's some extra material, extra labor, extra time to detail the R40 wall versus the R20 wall. A lot of different factors go into building this insulation out, as you all have probably run into. So we've done all that, and now our assembly is 6.2. We've gained a whopping not so whopping, I should say, 8% increase over 5.7. So instead, we're going to put a better window in. So wall insulation R20, same glazing area. But instead of the R3.3, we're going to use an R5 window. Now we've gone from 5.7 to a R8, so a 40% increase over. So this is just to show how significant, and I realize that 50% glazing area is pretty substantial percentage wise. But you can see that there's really a much more dramatic effect simply by using a better window than having to build out the wall insulation itself. So how do we get there? How do we get to that 0.20 number or the R5 number and below? Well, the quickest way to do that, or easiest, most efficient way, is to add another pane of glass. So instead of the dual pane, we are using a triple pane. So you can see here, let me pull my pointer up. Oop, there it is. As I as we look at the triple pane here, you still have a low-E coating is shown in red here. What is nice about the triple is now we have the ability to be able to add another low-E coating to the interior of the IGU. So we still number these again. So 1, 2, 3, 4, 5, 6. Now we have a low-E coating on surface 2, and we have the option, or not, to have it on surface 5 as well. In a dual pane system, thermodynamically, it's not advisable to have a low-E coating living within the IGU on surface 2 and 3 because one is a passive heating low-E coating, the other is a reflecting low-E coating, and it heats up this area too much. And so it's just not done within IGUs primarily for that reason. But with this barrier, you've got two separate areas, one being more influenced by what's happening outside, one being more influenced by what's happening inside. And as heat tries to transfer through, it's hitting not only the physical barriers, but also those gas barriers and the different elements inside. Why having a low-E coating on the inside is important, particularly with condensation resistance. I had mentioned before that condensation resistance is primarily a relationship between the relative humidity within the building as well as the surface of glass temperature. Low-E coatings are primarily a metal-based product. Sometimes they're single pass, sometimes double pass, sometimes triple pass, and even beyond. In a dual pane system, to get two low-E coatings, one is typically on surface 2, the other in what we refer to as a soft coat. The other is on surface 4 and referred to as a hard coat. The reason why it's a hard coat is for those who clean their windows. Obviously, they don't want it to wear off, scratch, those sorts of things. So being metal and being room side affects the center of glass temperature. So you have more of a preponderance of or potential of condensation. So typically when you have a dual pane with a dual low-E coating, your condensation resistance suffers because of that. Again, particularly in our climate area. I know just as an aside, to meet the Energy Star goal of the number one domestic glass manufacturer in the United States would require two low-E coatings from a solar heat gain perspective. So to the extent you got a Energy Star rated window, they did not recommend it for our area specifically because of condensation resistance or lack of condensation resistance. So something to keep in mind there. But as we add on, so this does, as I mentioned, a great job. We're breaking up those convection loops. So instead of one big convection loop, now we have two. Again, as we're trying to manage the heat transfer to the outside. As we add that, we're also adding weight. So we are going to have to use some typically bulkier frames. I'm sure all of you have seen the European like tilt turn frames, for example, a little more bulky than the domestic manufacturer frames with that house dual pane. But the other thing that needs to be considered is the weight. We're adding all that weight, so particularly on operable windows, we're also looking at upgraded hinging and hardware to support the weight of those operable sashes as well. But this is how we get to 0.20 and below. Um, as we take a look here, just again a snapshot. What we have on the left side is the U factor. It's converted on the right side as the R value. So really the more efficient are going to be done this left, or I'm sorry, right bottom quadrant. The IGU width is on the bottom on the horizontal axis here, and you'll see that this black line represents typical dual pane IGU width. It's about 3/4 of an inch, 11/16 is typically what most domestic manufacturers will run. As you look, we've got a solid blue line and then a dotted blue line. The solid lines here, and actually all the colors, are an argon gas fill, and the dotted lines are a krypton fill. So the blue lines represent a single low-E coating. The red lines represent a dual low-E coating. And the green lines are triple pane low-E coated. Again, with argon and krypton. You'll notice this typical dual pane geometry, the performance pretty much flattens out at 3/4 of an inch. And actually, you tend to lose a little bit as you go even as that gap gets bigger. Whereas in the triple pane or these green lines, you are still gaining thermal performance through an inch and actually even a little bit beyond to about inch and a quarter, inch and 3/8. So definitely a lot more potential with the triple pane from a thermal performance standpoint. So that's how we improve. But there's a couple of other things that we can do over and above the uh, adding the triple pane as well. And we talk about gas fill, which was referenced in one of the previous slides. So as I mentioned before, what we're going to do is from a convection standpoint, we're trying to slow down the heat transfer. And we do that by using gases that are more dense than air. Um, we started off with air. We are now on argon as the standard. Argon is very cheap. It represents about 1% of the atmosphere. So it's very readily available, easily used in manufacturing. Really, this is the standard. So much so to the point that the many times in automated lines, it's more expensive to say, you know what, I just want to go with air instead of argon. To turn off that function on an automated line is now a custom option. That's how standardized the industry is on having argon as a gas fill. And then we have krypton, which is about twice as dense as argon, a little less abundant, a little more expensive than argon. But if you had an opportunity to price those two out 4 or 5 years ago, there was a significant difference. There have been advances, not only in technology, but on the business side of things. There are some antitrust things going on. Krypton now is very affordable when you're looking, or should be affordable when you're looking at that compared to argon. But we use those, and if you take a look at the periodic table elements here, all the way over, this is the noble gas section. The noble gas section is the section that they're colorless, and they don't react with other chemicals. So it's very useful in a manufacturing setting when we are looking at um, yeah, using things that are that are going to stay pure in the manufacturing process. So you start off, you look at helium and then neon, both less dense than ambient air, so would do us no good. Then you have argon and then krypton. Xenon was used years ago. It is, as I mentioned, argon is about 1% of the atmosphere. Xenon is like 37 parts per billion of the atmosphere. Very rare, very expensive. They use a special, or they used to use a special cryogenics harvesting process for it. Um, there are other technologies that are out that are much more um, budget friendly, we'll say. So Xenon's pretty much been left to the back burner of IGU technology there. And then, of course, um, radon, which hopefully nobody's testing on Windows. Um, so that's the gas fill. Going back to the conduction and again, referencing back to when we're talking about the edge of glass performance, that's one of the three things that FIAS and other high performance systems will pull out and measure specifically. Uh, this is what affects edge of glass, the spacer. This metal spacer represents 90%, if not more, of what's out in the market. It's very easy to use, very easy to manufacture. It's just a stainless steel, flexible piece. It turns the corners. It's very easily manufactured and pliable so that it can, again, turn all those corners of the IGU. It's just simply put in a bed of silicone. And these white area here is desiccant. There is a little bit of weep system. So any incidental moisture that is in between the panes of glass in manufacturing can be pulled down and put into this desiccant area. However, as you can guess, metal is very conductive from heat transfer standpoint, and that's what we're trying to get away from. So thinking or looking back, and here's the picture of that thermal image that we had at the beginning of the presentation, you'll notice these dark red and orange areas are around the IGU. That's where this metal spacer lives. And that's why we're looking at better technologies other than metal when we're looking at edge of glass performance. Again, this is also a significant contributor to condensation resistance because we're talking about temperature versus relative humidity. So we now have and have had quite some years now, warm edge spacer. Primarily, it's a dense foam product, and as you can imagine, that foam product has a much less heat transfer than your stainless steel spacer does. And that's typically used within the high performance window range. But there's more. A subset of the warm edge spacer is the thermoplastic warm edge spacer. So the thermoplastic spacer, best way I can kind of describe it is it's almost like a hot melt glue that cures. And what happens is it bonds itself not only to the silicone bed, but also to the glass as well. So and again, when we're taking a look at our climate zone, um, that thermal expansion and contraction is happening with not only the window frame itself and that interaction between that and the IGU, but also the IGU itself. So as that flexes in and out with thermal expansion and contraction, the thermoplastic spacer moves with the glass. I'm sure everybody has had the experience of seeing a window that looks like it's raining in between the panes. That seal is broken. Any gas that was in it has dissipated probably long ago. Condensation is building up on the inside, but that seal has failed. So as you can imagine, when you take a look at a metal IG spacer bar, it's not going to flex with it, and that's typically where the seal failures happen. Ah, I just want to check the chat because I saw a couple of questions here. How long can heavier gases be expected to last in IGU? Great question. Um, it varies. Typically, they'll say anywhere between 1 and 3% per year of natural loss with the metal spacer bar. That's again provided that that seal doesn't break. Once the seal's broken, it's done. The thermoplastic spacer, that's actually one of the big selling points of the manufacturers of the thermoplastic spacer, gas retention. So they are saying less than 1% per year. Some naturally absorbs into the material itself. But when you take a look at the warranties of the thermoplastic spacer versus the metal spacer, I know on the commercial side of things, typically you'll get a 10-year seal warranty. Thermoplastic is 20 years. They've done advanced testing of 40 plus years, so that might even bump up. But take a look at the warranties, and you can really see, regardless, they typically won't warranty against gas loss. But that's what should be expected. I know that's a pretty long-winded answer there, but anywhere between 1 and 3% in a typical Windows scenario. And the slides, I can certainly make the slides available. Happy to send them to everyone. I know I'll be getting a list of the AIA numbers too. But if you want to share your email address, I'll share mine at the end too. And yeah, certainly feel free to shoot me an email, and I'll be happy to send those over. So we talked about where the industry was, kind of where we are. Now it's time to talk about some really cool new technology that's out in the marketplace now, again, in varying degrees. Vacuum insulated glass. I know this is making more and more of a push over the past couple of years. Really cool technology. We're seeing a lot of this in the renovation space. As I mentioned before, we all know there's there's a ton of single pane, non-thermally broken aluminum frame systems out there. These can get down to almost a quarter of an inch width. So when you take a look at a cross section of the vacuum insulated glass, you'll see here two panes of glass. There's this airtight edge seal that goes around the entire perimeter, and then a vacuum condition is created between those panes of glass. So, as physics will tell you, as heat tries to transfer through that vacuum condition, it's an excellent thermal performer. But again, it's a vacuum condition, so those um, panes of glass don't collapse on one another. There are little spacer pieces that are put in, little steel pillars that are put in to keep those out. So really fantastic technology. We see this a lot on the renovation side. One of the kind of the downsides of vacuum insulated glass is that it's very expensive. Most of it is being imported from Asia, and even in Asia, there's not a lot of it. Just to tell you how expensive it could be. It's also very dependent on this airtight edge seal, and this port. That's how you're gonna. That's how they're creating the vacuum condition in between. So, but typically this is, oriented top left or top right of the window unit. So it's kind of out of direct sight. Um, the other thing is just from a condensation standpoint, there's not a lot to work with when you're looking at insulating that edge of glass. And those spacers can be, not that it's big deal, but it could be an aesthetic deal. You see these little dots where my pointer is in the shadow lines. You may see some spacer pillars. If you're ever in New York and want to see this in action, the Tiffany and Company in their flagship store, they had beautiful original stainless steel window frames that they wanted to preserve, and they did, and they used vacuum insulated glass here. So again, they were replacing the single pane, just clear glass, and they used the Vigs and have real good thermal performance on that. You'll see here, this isn't from that installation, but you'll notice, before the original windows and then after, there is typically some heat loss on the edge of the Vigs, but your center of glass is certainly very huge upgrade over the single pane. And to fit into new construction, what happens is, and we have some manufacturers doing this here, that's available now. Um, they take the vacuum insulated glazing portion, add this leg on it, typically to fit into that dual or triple pane glazing pocket, um, and add that in. Again, this is going to be for a new construction window, that we can get that VIG technology into the domestic new frame windows. It doesn't add a ton of thermal performance, but it allows the product to be more universal to use. It's also adding another layer of expense onto it, but um, tremendous insulating factors. You can see here, vacuum insulated glass, your performance range anywhere from R7 to a R21 center of glass. Moderate scalability, again, just because not a lot of manufacturers are doing it. And dimensions you can see there. Yeah, see almost a quarter of an inch. Um, that's going to be for just the VIG up to an inch. That's going to have the VIG hybrid with the extra leg on it. But very costly as of right now until we get our manufacturing efficiencies up. Next, aerogels. I don't know if you have heard of aerogels. If you have, it may have been from the space industry because that's where this is used a lot. It's a super insulator in a very thin format. It is the lightest solid. It's like 95% air, but it is still a solid. There's actually a company, um, well, it started off at MIT. A group of researchers were trying to, and if you take a look at AeroShield, it has this cloudy look to it. Obviously not really conducive, except for maybe, I don't know, bathroom window. But to get that clarity, a group from MIT really worked on chemical treatments, temperature, pressure, and they've got it really to this format here, which it looks really good so it can be used in window format. The same idea still applies. We're trying to fit it into that dual pane system. So when you take a look at a cross section, you've got the glass, the aerogel, which again is the solid. You still have a gas fill area and then another piece of low glass. So again, as heat tries to transfer through this additional solids, really super insulator, which is used. I had mentioned NASA; they use it on like thermal blankets on spacecraft. Now in the window area, but those group of researchers from MIT have started a company actually based in the Massachusetts area, and some really good promising results from that. Great thermal performance. Again, downside on this is the price. There's just not a lot of people manufacturing it. It's a great insulator that works very well within windows. And once the demand in the manufacturing gets there, this is going to be hopefully a really good option. One of the things, and also with VIGs to a lesser extent, but the size of the units as well. I know they're working really hard to get much larger square foot pieces of glass with this as well. But when we take a look at kind of that aero view of aerogels, R7 to R20 center of glass performance, again, fantastic thermal performance to fit into the domestic conventional dual pane footprint. Again, moderate scalability, just not a lot of people doing it. And right now it costs a lot, but really great emerging technologies that are in the market, and as they make more progress on that, even better um, solution. Then last, we have thin glass. So thin glass is pretty unique in that instead of using that conventional triple pane system, a piece of thin glass is used. Where does the thin glass come from? Well, the thin glass is the same glass that is on your smartphones, flat screen TVs, half a millimeter to 1.3 millimeters typically, instead of the 3 millimeters where traditional glazing starts off. So you still get all the benefits, and they found that you don't need that thick piece of glass to have the same thermal performance as a conventional triple. That convection loop is still broken up by the piece of thin glass. The thin glass is actually more flexible uh, than the thicker inner and outer lights. Um, and there is no structural uh, load on it at all. So chances are that's not going to break. The other panes will break first. Still allows for the two low-E coatings on the interior as well. And that can be used for renovations, new windows. This you see here, this is a triple pane. The triple pane thin glass can be in as small as a 3/4 inch pocket, which is the traditional dual pane system. And then a quad pane can fit in as little as a 1 inch pocket. So a lot of flexibility there. It's made in a different process. You have your typical soda lime float process. This is a vertical fusion drawn process. Corning is the primary supplier of this, but it's a stories high uh, uh, glass waterfall, for lack of a better word. But as it moves down, it actually cures, and then the pieces are cut off, and you have you can get 50, 60, 70 square foot sheets of the thin glass. So very versatile. So you've got uh, really a larger area that you can work with when comparing to Vigs or aerogels. The other thing is the weight. So I had referenced before, particularly in operable units or just installing windows, installing very heavy windows and all the machinery and manpower that it takes. You can imagine you're almost saving a third because on a triple pane system, from a weight perspective. So large potential for larger operable windows without upgraded hardware and hinging. Not as bulky of frames in many cases. So a lot of benefits to the thin glass, and this has been in the market for a decade. There's been a lot of work done with Berkeley National Labs on this as well. And there's really a partnership with the Department of Energy on it as well. So real good from a cost perspective in particular. So when you take a look at the uses, as I mentioned, retrofits, new windows, but also interior store windows, same performance range as the um, aerogel and the Vigs at a much less cost. The dimensions, it's again very flexible. We're not, nothing is being taken. Well, I should say it's glass. So it's just glass taken from one industry being brought into the window industry. So there's not a lot of special knowledge, special tools, special machinery that has the potential to drive up that cost. So it's very, very budget friendly and very, as you can see, performance wise, high performance minded. So when you take a look, cost versus performance, you take a look here, the VIG hybrids, VIGs, aerogels on the more costly side, great thermal performance, but right now, really, on the pricier side. Whereas you take a look at thin triples and conventional triples, the thin triple, really, when you take a look at conventional triple, for most manufacturers, Europe's been doing it for years. They're pretty much standardized on triple pane. Here domestically, the industry is just standardized on dual pane. So to go to a triple pane is a custom feature. Most of the manufacturers that manufacture thin triples, though, or thin quads, have standardized on those. That's why the price is very comparable between the two. Um, with all that said, and I really appreciate the time. I know we're running up on it here. There's always a lot of considerations for high performance glazing. You see some of them listed here. I know budgets a conversation on every single project. Yet to have run into one that it's not. But also, nobody wants to be the guinea pig either. So, there's always that balance to it as we kind of move in. But those are why glass, in particular, in windows are very important to the building envelope as a whole. So, with that, I really appreciate the time. And I'll turn it back over to Keegan and Sarah here.
Sorry, I was talking to mute. Luke, thanks so
Oh,
much. Yeah, that was really, really informative and interesting. Thank you. There is one question, and we'll see if any others come in. Folks, if you want to put your questions into the chat. How long can heavier gases be expected to last in an IGU?
yes. So, touched on that a little bit before. Typically, they'll say with a typical spacer, 1 to 3% is lost per year. That's provided that the seal stays intact. A lot of the thermoplastic IG spacer are saying that it's less than 1% a year for them. So it really depends on the IG spacer, the IGU manufacturer, but that's just a general kind of rule of thumb. With that said, you'll be hard pressed to find a warranty where, and I think that the thermoplastic spacer will be the first group that will do it, actually warranty with gas fill. But right now it's not something that's really included in anybody's warranty.
Um, Great. Yeah, thanks. I think that's the only unanswered question. I'll just reiterate that the recording of today's session will be available on the Build Green Connecticut video library afterwards. And for folks looking for the AIA HSW CEUs, we will get certificates out to everyone to get those entered in. And Sarah, thanks for putting that in the chat as well. Just a reminder for folks that we do have another session coming up in this series on June 9th called Pushing Boundaries, Applying FIAS Core to Internal Load Dominated Buildings, which is both FIAS and AIA approved for CEUs. So looking forward to that session and seeing everyone there. Um, and Luke, thanks for putting your email there.
Yeah, it just
Yeah, appreciate you offering to
yeah,
take questions if anyone has a follow-up. If there's no other questions, I think we can conclude for today.
sounds great. Well, thank you,
Luke,
Keegan and Sarah both, and all the participants.
yeah.
I really appreciate
Luke,
the
thank you
time.
so much. We appreciate you
Yes,
joining us, and
of
thanks,
course.
Sarah.
Thank you.
See y'all soon.
Thanks,
Bye.
love.
Bye.
Bye.
Bye.